electron. I've got to record, so I just started recording. So for sharing of electrons, what we usually do is that we draw the electrons in dots and crosses. And what literally happens is that these atoms come closer, so much so that their shells start to overlap one another like this. And in that overlap are those electrons shared. So a dot is here and a cross is here.
Yeah.
So what happens, let me explain this. And this is not a part of work, what I'm about to say. Exactly, that's not a part of O levels either. It's actually a part of A levels. But I'm going to say that just to make sure that you understand the whole thing. Now, this sharing, these set of electrons actually move through the structure in this way. They start moving from here, they revolve all over here, and then they revolve over here, all over here, like this. So they move like this. Now, with this speedy movement through the structure in this way, actually gives both the atoms stability, or both the atoms a feel of that they both have 2 electrons each. Get the point?
Yeah.
So, simply speaking, they both uh, think that they both are stable. Why? Because having 2 electrons in the outermost shell, helium has 2 electrons in the outermost shell, and that's why helium is stable. Now, helium has 2 electrons in the outermost shell. That's the nearest noble gas configuration. And both the hydrogen atoms think that they have the configuration of helium, and both think they are stable. What do? A dot and a cross is actually shared as a single line. So instead of doing this, we may write it like this, or we may write it with a simple line. That's how we write it.
Mm. Okay.
Okay. So
Yes.
the sole point of this practice is to bring the dots and crosses in a sharing. Number one, in a mutual or equal sharing. So if one atom shares a dot, another one would share one cross. If one atom shared 2 dots, the other one would also share 2 crosses. So they are going to equally share the electron. That's how they get balanced. One, two, whatever they are short of for the arrangement of the nearest noble gas, be it 2 electrons, be it 8 electrons to become stable, they'll do so. Now, we do understand that nonmetals have either 5 electrons or 6 electrons or 7 electrons in their outermost shell. The ones with 7 electrons only need to share one more electron, and their octet would be complete. The ones with 6 would need to share 2, so that 6 plus 2 is equal to 8, and that's how their octet would be complete and they would be stable. So that's what we are about to do. All right?
Yeah.
Okay, let's start with group 7. For group 7, we have, let's take chlorine as an example. Now, chlorine has 7 electrons in its outermost shell. So when you draw it, you can draw it like this: 1, 2, 3, 4. You may draw it on the lines, you may draw it inside the lines. There are both ways that you can draw it, and both ways are actually correct. Right? So, like this. So, 7 electrons in the outermost shell. The compound is HCl. It's actually a single bond between hydrogen and chlorine. Hydrogen, on the other hand, has just 1 electron. Let's draw it like this. So what's going to happen in this case, that hydrogen would share its only electron and chlorine would share its single electron, so much so that they are going to overlap one another. I'm going to draw it like this. Since the size of hydrogen is smaller than chlorine, so there you go. Now, in the circle of chlorine, how many electrons can you count? 1, 2 dots, 3, 4 dots, 5, 6 dots, 7th dot in 8th cross. So
Yeah.
chlorine has its octet complete. Hydrogen, on the other hand, has its duplet complete. So that's why they bond. They bond because they both become stable after bonding. After sharing one electron each, one of them gets to have their, and I got to go now, right? Just give me like 3 to 4 minutes, okay? Share the recording. All right. So that's how they become stable. And that's why we show it like this with a single line. You may show these electrons separately on the structure, or you can leave it like this. That's entirely up to you. Now, in case of group 6, let's suppose if we try to combine group 6 element with it. For example, we have oxygen in group 6. Oxygen has 6 electrons. Since it's a part of group 6, of course, that's the number of valence shell electron it would have. So, like this kind of structure. Now, when oxygen is going to combine, it would actually require 2 electrons instead of 1. Take a look, it has 6, it requires 8, so it has 2 more added to the same structure before it can become stable. So what happens is that it would require 2 hydrogen atoms to get balanced.
Yeah.
So what happens is that I am going to change it somewhat to this form, like that. Okay, so
What if it's from group 5? So then it will need like three
three
electrons.
three electrons to get balanced. You're right about that.
Yeah, okay.
And that's
Understood.
how it becomes the structure of water. So that is this, this, this. You may show it like this, or you may show it like without the electrons, like this and this. All right?
Yeah.
Right, just give me a second.
Sorry. Yeah, okay.
Yes, you were saying?
Can you give me a question so I can do it by myself and know?
Yeah, sure. That's what I was about to do. So what we're
Yeah.
gonna do is that I'm going to erase these parts. Okay. And since you have examples at the bottom, and since you just discussed with me about group 5, so that's what we're going to do. All right. So what I'm going to do is that I'm going to give you an element from group 5. You're going to attach it with a few hydrogen atoms. You're going to attach it with so many hydrogen atoms, as many as are required to balance or to make that atom stabilize.
Yeah.
And that's how it's going to work. So we're going to work with group 5 as well. One element from group 5. We're going to work with one element from group 4 so that you can actually practice both of these. So we're going to take nitrogen from group 5, and nitrogen has 5 electrons in its outermost shell, right? So
Yeah.
you can start from here on onwards.
Yeah. Okay.
Attach it to as many hydrogen atoms as you need to balance and complete the octet for nitrogen atom. Okay?
Yeah. Sir, I'm done with the nitrogen, group 5.
Okay, either send me the picture or tell me that out loud.
I'll tell you aloud, okay?
All right, go ahead.
Okay, so in the outer shell, we will have 3 electrons, and okay, wait, I'll say it briefly. Okay, so in the first shell we will have 2 electrons, and in the second shell we will have 3 electrons. So in order to it to be stable, it needs 8 electrons. So we have to add 3 electrons. So hydrogen will share its electron with non-hydrogen. So um, yeah, it will share 3 electrons with nitrogen.
Okay, so that's what we're gonna do. Nitrogen shares one electron with one hydrogen, then the second one with another hydrogen, and the last one with another hydrogen, like this. The only thing you're wrong at is that nitrogen has 2 electrons in its first shell, and it has 5 electrons in its outermost shell. And on top of those 5, it would get 3 shared electrons from 3 hydrogen atoms. And that's how the structure of ammonia completes. You may draw these dots over here. And then we have one bond of hydrogen over here. Sorry, not like that actually.
Wait,
One,
so
one over here, one over here, one over
yeah.
here. That's how we form it. What you're supposed to do is to look out for every circle. If it's a circle for any other element except hydrogen, it would not be just 2, it would be stable with 8. For hydrogen, it can be stable with 2 electrons only. For the rest of the nonmetals, they would be stable with 8. So take a look at the circle of nitrogen. It has 8 electrons, 3 crosses, 5 dots is in the central diagram.
So in nitrogen, the first shell will be having how many electrons?
Actually, the first shell of nitrogen has 2 electrons. It's the second shell or the outermost shell, valence shell, which we also call it, that has 5 electrons and that actually shares in covalent bonding. Remember, inner shells stay inactive during covalent bonding. They do not share electrons. They do not participate in covalent bonding. So
So
you're not
we
supposed to say it out loud. What you did back there is that you told me that there are 2 electrons in the first shell and then there
yeah.
are 3 electrons in the outermost shell. That's not correct entirely. There are 2 electrons in the first shell. There are 5 electrons in the outermost shell. And out of those 5, 3 actually bond with or make pairs with 3 electrons from hydrogen, 3 hydrogen atoms differently. And then that's how it's formed, right?
Yeah. Okay. Yeah.
So these 5 electrons are actually from the outermost shell of nitrogen. Remember, the structure of nitrogen is something like this. The first shell has 2 electrons, and right now I'm drawing the electrons with crosses, and that's easier to understand. The second shell has 5 electrons, like this. All right. So I
Yeah.
only drew these 5 electrons over here in the form of dots. I never drew the inner shell since that does not participate in covalent bonding.
So we
Make
should
sense?
not draw. Okay, so we should not draw the first shell. We should only draw the outer shell.
Yeah, we are not supposed to draw any of the inner shells. That may include first, that may include second, whatever the case may be. For example, in fluorine, there are 3 shells. The third
Yeah.
one is the one that has 7 electrons. So I never bothered to draw the first shell for fluorine or the second shell. I only drew the third shell, and from there on onwards, I continued with my covalent bonding dot and cross diagrams.
Yep. Okay. Now
So
I
we
understand.
are only supposed to go with outermost shell. And the good part about outermost shell is the outermost shell number of electrons and the group number is actually the same. So if its fluorine is present in group 7, it has 7 electrons in its outermost shell, and from there on onwards, you can easily decide how many electrons it's going to share to complete its octet. Octet means 8 electrons. So that's pretty easy.
Yep.
It does not matter how many total shells chlorine has, because the inner shells are not going to participate in covalent bonding. It's just the outermost or the valence shell that participates. So it's the only one that we draw. Make sense?
Yeah.
Good, great. So I am going to give another example to you. Let me raise the structure of nitrogen, and we're going to go with an example of an element from group 4 bonding with hydrogen. And the easiest of examples from group 4 is going to be carbon. Now, carbon has actually 4 electrons in its outermost shell, so I tend to draw all 4 on all 4 sides. That is carbon. Now, to complete its octet, 8 electrons, and to become stable, it would bond with a certain number of atoms. Go ahead, find that out, and when you're done, say it out loud.
Yeah, I'm done.
Okay, say it out loud. What have
I'll
you thought for?
I'll send a picture.
Sure, send a picture. That's fine.
Because when I say it loud, then I'll say गलत बोलूंगी.
It's all right. Even if you add a few more things to it, that's fine.
No, no, it's fine. I'll just send the picture. Um. Okay. Just tell me whether my way is correct or not, because I have done in another way. It's not the yeah. Okay.
Now, this time it's much better. There is the one small mistake. Remember, both the dot and the cross are supposed to be in the same overlapped part. Notice,
Oh
my dots
yeah.
and my crosses are in the same overlap parts. Can you try it again? The
Yeah,
rest is
yeah,
fine.
yeah, 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 okay.
And your overall idea about the number of atoms and how the straight lines are to be shown is perfectly correct.
Okay.
All right. I'm waiting for another picture.
Yeah, yeah, sure.
Take your time. That's fine.
Yeah, okay, I'm sending the picture.
Sure. Perfect. Now that's actually a perfect picture. Now, what you did back there is that I don't know why I am drawing my circle in such bad shapes. Let's try to do it correctly this time. So yeah, what you did back there was a dot and a cross together with four different hydrogen atoms. So those were arranged at four different points around carbon atom. There you go. And that's how we complete the duplet for all four hydrogen atoms, and we complete the octet for the carbon atom. See, you have four dots and four crosses around carbon atom, which means eight electrons complete, and the structure can be perfectly shown like this. So four hydrogen atoms, and that's what we do. So for
Yeah.
most common books related to this covalent bonding, your book, the reference book, you're going to find the same examples. This is the example for methane. This is the example for ammonia. This is the example for water, bottom right and or bottom left. We have the example for hydrogen chloride or hydrochloric acid, whatever you'd like to call it, since it's the same compound when dissolved in water forms the hydrochloric acid. So that's what we have. And these are the most common examples of covalent bonding.
Okay.
If you think you're good with practice, that's okay. If you think you need a couple of more compounds, let me know. We can always try more compounds.
Yeah, you can give more compounds because
Uh,
every compound has a different group number, right? That's why.
right. Okay. So let me just export this as an image. I'm also
What
going to
if
share the
what if
image with you.
what if they won't give anything from group H, right? Because it'll be already stable, right?
Right, perfectly right. Group 8 is already stable, so they don't give it anything from group 8.
So
That's
only from
correct.
group 1 to 7. Okay.
Right, that is correct.
Okay.
So you have one element from 4, 5, 6, and 7. You're going to combine them all with hydrogen as a part of your practice. Go ahead, take your time. You can do one at a time. You can do all four in the same time. It's entirely up to you. I'm here.
Yeah. Yeah, sure. Yeah.
In chemistry, for example, you have drawn it like this, and now it's perfect. But when you draw it over here, you do it like this. Now, in chemistry, this line, this line, this line, this line, all right, and
Yeah.
any other kind of arrow that you might come up with already exists in chemistry and has a different meaning. This one has a different meaning, this one has a different meaning, this one, so on and so forth. So we cannot make a single small change to a symbol that we commonly use in chemistry, right? Because this
Yeah.
might mean something entirely different. This is another type of bonding to draw an arrow. So you can
Oh,
never draw arrows. So doing something like this tells your examiner that you are actually trying to tell him about a different kind of bonding. And so far, you haven't even done that kind of bonding yet, which includes arrows and not just lines. So
oh, okay.
make sure that you do not draw an arrow,
Yeah.
right? Since they
Yeah.
have different meanings. And trust me, there are so many arrows in chemistry, there are so many different symbols in science. And most of the time, when you come up with something like this, that already exists in science and has a pretty different meaning. One thing. Second thing is that when you draw this entire structure, I've seen you draw it like this. Now I'm gonna do it over here since That's going to be easier for me. And we have done something like this. And then
Yep.
instead of drawing them here in the form of, well, what you should do is that you should draw them in a pair at one point. And
Uh,
what you actually did is that you drew one of them over here and one of them over here.
Separately.
Never draw them separately. You do
Yeah.
it like something like this. But that's, let me tell you, that is incorrect. You're supposed to draw the electrons in the form of pairs. Now that's actually how they exist, at least how we represent them.
Yeah. Okay.
All right. So
Yep.
that's the only two things what I can see from here. The rest is perfectly correct,
Okay.
which is really great, by the way. So you
Thank
understood that you are supposed to do this with, in case of silicon, and this is actually SiH4. This is pH 3. You understood that this is going to be like this for the structure of HF. You understand that this is going to be H2S, and it's going to be something like this. All right. So whether you
Yeah.
draw their pairs, these pairs on it, or whether you don't draw in them, that's fine. These pairs have their specific names, and we're going to do them a little later in the same part of the chapter. All right. So that's what
Yeah.
I gave you as examples, and I'm happy that you did it right. All right. So I'm going to
Yeah.
draw a diagram. Let's export it. Okay, good. So
Metallic